Welcome to this Center for AI Fundamentals talk seminar series. This time we have Dr. Rishideep Roy, lecturer in statistics from University of Essex. He recently joined Essex, and here we have.
Thank you. So, many thanks, Randomly, for the invitation. It is indeed a pleasure to come here and give a talk. It's a challenge to speak in an AI fundamental seminar, given that I'm going to speak about something in statistics. I'll try to present it in a way that maybe it is acceptable to an audience of AI. So this is a joint work with, I was previously working in India in an institute called IIM Bangalore. So it's a joint work with my colleagues there, Professor Shubhaputo Dash and Dr. Shodip Deb. So it is about electoral predictions. So what we are going to speak about is electoral predictions using multinomial data with randomly varying probabilities. And what they really mean, it will become clear as we go on in the as we go on. So we are all across the world. We are probably there are more countries who have democracy as a system of governance. So it's something that has been in focus for a long time. Democracy, through different mathematical results, has been shown to be least effective to, it is supposed to be least affected by external aggression. So since it is, the decision-making depends on a lot of individuals. So with the election process and that is fundamentally linked to democracy, there is an increased role of interests in electoral processes. And especially with the increase in media and a lot of surveys being done all across the board, we see a lot of electoral predictions. And there is a huge market for that. And there are a lot of TV programs that are run on electoral predictions. And so we are focusing on electoral predictions, but there can be different kinds of electoral predictions. What our goal today is going to be calling an election on the day of counting. So as the counting progresses in the morning, so like sometimes it can take a long time, like days, and there can be a lot of ambiguity in terms of what the result is going to be, even when the progress has been made for a sufficiently long period of time. So we are trying to make some electoral predictions on the day of counting. Now, our assumption is that votes are counted in batches, and during that process, we want to statistically predict the final results as the counting progresses. So when I say that we try to statistically predict something, it means that it's not necessarily mathematically predicting something. So a way of mathematically predicting would be, you have, say, 500 votes in total, and 400 have been counted, and we see that one has received 300 and the other has received 100. So you know that no matter what happens for the rest 100 votes, one of the candidates, the person leading, is going to win. So that's mathematical certainty that this person is certainly going to win, and that's how generally elections are called, when you have a mathematical certainty. But what we want to do is we want to do it through statistical prediction. So we might be wrong. We'll try to minimize the chance, and as well we want to predict as quickly as possible, okay, from the pattern. So essentially seeing the patterns and trying to make a final call based on that. Our model is essentially a time series model where the data is coming as votes, and we treat the model as multinomial distribution, and we collectively take some of the votes, some of the sequence of votes, we take it as a multinomial distribution. I guess most of you are aware of what a multinomial distribution is. It's a generalization of binomial distribution where you have multiple options. So our data is based on election prediction in India, where you have first past the post democracy. There are multiple constituencies, so it's kind of similar as what you have in the UK. And in our prediction, in our model, we assume that so multinomial distribution assumes that there are certain probabilities associated with every category, which is every candidate. We assume that the probability of individuals voting for one of these candidates, they fluctuate across batches. Okay. Now, there are many other potential applications of our model. We have ourselves done a few as well. What we did was about forecasting sales of different brands under stress situations when there is a shock in the market. So we predicted market shares of lozenges and how it was affected by COVID. There are many other potential applications of our model forecasting sales of different brands in general. Within game prediction in sports, who's going to win and who's going to lose. Predicting number of changes in the stock market movement, all of these are potential applications of our model. Now, this model that I'm talking about, what is that? We assume that for a multinomial data, there are a number of trials. So that means, what is a multinomial data like? It is an observation where you have C categories and you choose one of them. Every data is a selection of one among C categories. So that is the number of candidates. Every individual voting can vote for one of the C candidates. And there are K copies of multinomial random variable observed in K number of instances. So this is the batches in which we collect the data of elections. And we also assume that the number of trials in the jth batch is different, so it's not equal for every batch. So we assume that there are nj many observations in the jth batch, and in total there are k batches. And we also assume that the cumulative number of trials till the jth batch of the jth instance is capital Ng. And the total number of trials, that is capital NK, because there are total k many instances. So that is the total number of trials. Now, we have some observations of counts or votes for all the different candidates. So for each of the C categories, we have observed counts. This is the multinomial observation for the jth batch. So that is given as xj. Of course, you know that if the total number of trials for the jth instance is small nj, then sum over this x1j plus x2j plus going up to xcj, that will equal small nj. Okay. And yj shall denote the cumulative counts till the jth instance. So that means yj would be the sum of the xj's. X1 to xj, that is yj. And for each of the different candidates, the total number of votes till the jth instance would be sum over xci and equals 1 to j. And then the probabilities. These are important. So the probabilities for the C categories or the C candidates for the jth instance is P1j, P2j going up to PCJ. So this is a general form of the probabilities. Now, naturally, the sum of these probabilities will have to be 1 because every voter has to select one of the C candidates. And we make certain assumptions about these probabilities. So what we assume is that these probabilities are random variables and they are fluctuating around a certain constant. So that constant is PC. So for the Cth candidate, for the jth instance, the probability of any voter selecting them is PCJ, and PCJ can be modeled as PC plus epsilon Cj. Now, what do we assume about these epsilons? Well, we assume that they are mean zero random variables for each of the categories till capital C minus 1. Why is that? Because you know that the last one, I mean, the sum of all probabilities has to equal 1. So we cannot put restrictions on each of the different categories, because even ultimately for the jth instance, the sum of probabilities have to equal 1. And we assume that sum over PC, C equals 1 to capital C, that is also 1. So as a result of that, we make a restriction, which is the final random variable epsilon Cj, the final fluctuation is negative of sum of the rest of them. Okay. Now, for our convenience, we define these vectors Pj, which is all the probabilities for each of the candidates together, and epsilon j as all the fluctuations for all of the candidates together. Now, for these epsilons, as I said, we assume that each of them have mean zero. And further, we assume that their variances and covariances are of small order 1 over nj. Okay, so as nj increases, this goes to 0. Now, under this assumption, we propose our model, which is a model for all the votes cast at the jth instance. And that follows a multinomial distribution with number of trials small nj and the probabilities being given by pj, which is also p1 plus epsilon 1j, p2 plus epsilon 2j going to pc plus epsilon cj. This is for the jth instance, and we further assume that each of the different instances, the data that we have for each of the different instances are independent of each other. And the epsilons follow the assumption above, which is they are mean zero and variance and covariances are small of 1 over nj. Now, under these assumptions, we can find basic moments like first order and second order moments for the votes cast for every candidate. So their expectation is given by njpc, which is like what it would be if there are no fluctuations, no randomness with epsilons. And the covariances are also given in a specific form. These are quite similar to multinomial variances and covariances. Now, this is their expectation for like the cumulative votes cast till the jth instance for say the cth candidate, and that, I mean, the only change, as you can see, is in the n's, which is capital NG, which is the cumulative vote count. And that's also quite natural because, as you see, there is no effect of the epsilons in the expectations in the first instance. Okay. Now, what we are interested in is making predictions. So we have to estimate who is going to win the election. Now, winning the election also naturally means that their proportion of votes will be the maximum. Okay. Now, so we are essentially interested in the parameters, which is P1, P2 going up to P capital C. Now we know that P of capital C is 1 minus some of the rest of the P's. So we are currently focusing on the first C minus 1 categories. An estimate of these can be obtained based on every instance. And we have a result about these estimates. So this comes from multinormal approximation to multinomial distribution. So this is kind of like central limit theorem. So as you know, for a binomial distribution, a central limit theorem is like the normal approximation to a binomial distribution. So this is kind of similar. So what we have is a convergence in distribution when the batch sizes, each of them, go up till infinity. All right. Now we are, as I said, we are interested in the parameters P1, P2 going up till PC minus 1. And the estimates are given by sample proportions, as I showed in the last instance. The estimates are x1j over nj, x2j over nj, and so on. These are sample proportions for each of the different instances. Now, when we make predictions using them, then the complication that we face is that the variance of these estimates, as I showed in the last instance, the variance of these estimates are dependent on the parameters themselves. So and this is a phenomenon that we observe in binomial distribution as well, which is like if you want to estimate a proportion, the proportion of heads or tails in the number of tosses, for example, that will involve, their variance will involve the proportions themselves. So a way of tackling this while making an estimation, making a prediction in future is transforming the estimate. And we will transform the estimate in such a way that the variance of the transformed estimate is a constant. So we take a function of our estimates and work with them. And the variance of these functions will be a constant. This is what we call a variance stabilizing transformation. Okay. So the variance stabilizing transformation for proportions is given by sine inverse of 2 times proportion minus 1 divided by 1 plus 2a over nj. Now, this a can be any positive constant. Generally, in our calculations, in this specific instance, we have taken is as 3 by 8 is just one positive constant. And then the advantage that we have is that we don't have parameters anymore in the variances, so we can make predictions using them. So now, based on the transformed parameters, we again have a form of a central limit theorem, which is square root of nj plus half times nj minus mu, that converges to a multivariate normal distribution. Okay, so now we shall work only with the mu's, which are transformed parameters, and the transformed data, which comes from transformed sample estimates. Okay. Now we will use a Bayesian framework in our estimations. So we assume that there is an underlying mean and true covariance matrix, which is again a function of our original parameters. So that's what we want to estimate. And then the result that we have regarding them is the posterior means for mean and variance, because now we are working with a multivariate normal distribution. The posterior means they will converge to the true underlying means and covariances. Okay. In our Bayesian framework, so we use a hierarchical Bayesian framework, and in there, we assume conjugate priors. That's again for easing of our computations. Now, I'll come back to the theorems and the proof of it, but before that, I'll just talk about the data. Okay. So the data that we have is data from a specific state and in an election in India. We've used another instance of this data for making predictions about US elections in 2016, depending on votes from different counties. I'm not presenting that, I'm only presenting the data that we have from Indian state elections. So we use our methodology that I briefly described to call elections. The data we have is round-wise data from Indian state elections of 2020, and we focus on 2 dominant categories. So there were few alliances. So essentially there were 2 dominant parties, and the rest of the categories were not really that important in it. So what we assume is that the individual probabilities for the three different categories, they are random variable for each of the counting rounds. And we want to estimate the probability, the parameters for each of the three different categories, and whichever is going to be the highest, that is the one that's going to win that constituency. So the probability of winning for every allowance is counted at the end of each round. So we would find the chance that one of these proportions is a dominant one. And in our electoral calling, we allow at least 50% of votes to be counted before we make a prediction. This is what we say, too early to call. So like, if we do not have enough volume of data before making a prediction, that might bring in some errors in our prediction. So this is something that we avoid there. And the other is, we have to be at least 99.5% confident of the winner. Okay. And the predicted winning margin has to be at least 5% of the remaining votes. Okay. So we can ensure all of that because in this data, we know the total number of votes cast. We also know the round-wise counting. And based on our model, we can find the probability that one of the proportions is going to be higher than the rest of them. So we have to ensure that that probability is at least 99.5. And based on this probability, so at every round, at the end of every round, we have a prediction of, we have an estimation for these probabilities. And based on these estimates, we can also find an estimate of the final winning margin because we have the total number of votes. If we have an estimate of the different categories, then the winning margin would be the total number of votes times the difference between the parameter estimates of the two dominant categories. Okay. So we have an estimate of everything, and based on that, we can make these selections. So whether we have counted at least 50% of the votes, and also whether we are 99.5% confident of the winner, and also whether the predicted winning margin is at least 5% of the remaining number of votes. And this is our forecast. So the ones in green, so what we have is a shapefile, and on that we have predict, and I mean, they are essentially a demarcation of all the different constituencies in a specific state in India. And we have 3 different colors to demarcate the constituencies: green, red, and blue. So blue means we cannot make a call. Now, as I said in the previous instance, we have 2 restrictions, which is too early to call and too close to call. For these blue constituencies, we are never able to cross this threshold. That's why we cannot make a call for 2 of them. We have some red ones, which is ones where we make a wrong prediction. Now, a wrong prediction can happen in different ways. It might happen that there is a specific pattern that is followed in the first 50% or 60%, and that trend completely reverses. So even when we are certain that, like more than 99.5% certain that this person is going to win, they might lose. Okay. And of course, there are green ones, which is where we are predicting correctly. Now, the graph on the left-hand side is depending on, I mean, the color, the density of the color is depending on the percentage of vote left when these calls were made. So ones that are solid are the constituencies where the predictions were done quite early on, when the percentage of votes left was like between 40 and 50%. Okay, and we can see that most of the constituencies, the colors are quite solid. On the right-hand side, it is about final lead. Now, of course, not every constituency will have the same number of voters, so the numbers might not reflect something, but then again, like as you can see, if the margin is quite high, then maybe it is we can call it quite early. Okay. Now, as you can see on the right-hand side, the very lighter ones, that is the constituencies where the final margin of victory was pretty low. Even there, we have done a good prediction because most of the lightly shaded ones are also green. So we have made correct calls in, relatively correct calls in them as well. Okay. And the prediction accuracy of our methodology. So in the prediction accuracy, what we do is that we categorize the constituencies depending on the final margin. Now we see there are seats where the final margin is less than 2,000. We have made more incorrect calls in them. For the constituencies where the final margin is more than 20,000, there are 83 such constituencies, and among them, we have made 83 correct calls, so no incorrect calls. Among the constituencies where the margin is between 10,000 and 20,000, we have made one incorrect call. Now, for the seats having more than 20,000 margin, the average counting, that means when we are making a call, the average vote counting there is 51.9%. So we have put a restriction of at least 50%. So after that, we are making a call quite early on. As we see a similar pattern for the 10,000 to 20,000 thing. So that's again 55.2%. For the ones where the margin is between 5,000 and 10,000, we have 4 incorrect calls. And by the way, like in a constituency, on an average, like as you can see, there are around 170,000 votes per constituency. On an average, there are 170,000 votes, as you can see across the board, at least 170,000. Okay, so it's quite large in number. So 5,000 to 10,000 is not bad as compared to the total number of votes cast. Now, where we go wrong is the ones with smaller margins. So 2,000 to 5,000, we have 4 incorrect calls out of 29. And when the margin is less than 2,000, we have 5 incorrect calls out of 23. And there are 2, yes.
I have a question. So from these numbers, can you give a judgment about how close are you to hitting that central limit theorem point in these numbers?
So central limit theorem so the central limit theorem that we are using is for multinomial distributions. Now that doesn't require a lot because for each of the proportions, they are well represented. So what we have ensured is that on the rest of the non-dominant players are blocked into one group. So for a multinomial central limit theorem, what we require is N to be large, not, more than 50, which is quite evident here, or 150, and each of the categories being represented sufficiently well enough. We also have that. So we are, our assumption of normality instead of the original distribution, which is multinomial, is satisfied.
Is that quantifier that
So the distance between that, like the actual distribution and the multivariate normal is quite low. Like,
how do you do
no, because because there is a quantification of like when can we apply a like a multivariate approximation to a multinomial distribution. Now, these numbers are way above those numbers. So the prediction, the inaccuracy is not because of our distributional assumptions. The inaccuracy is because of changing patterns. I'll go into specifics of some of these errors that we make. So it is not because of the distributional assumptions or because, so I mean, I have skipped that part, which is the Bayesian approximations and posterior predictive distributions. They are again based on multivariate normal distributions because we were using conjugacy. So all the predictions will be based on multivariate normal. So it's, I mean, of course, when we are making a prediction that has a variance, so that has a standard error of prediction. So there is, of course, some error there, but these
you could have done uncertainty quantification here, right? Because you have a central limits theorem, you could have done uncertainty quantification.
Right, so I could have found like there are many metrics to measure whether this is.
Telling us standard deviation of the.
So I do have I do have all of that. It's just that I haven't shown you. Yeah. So this is a covariance of the posterior predictive distribution. These are our variances. So I have skipped it. I'll come back there. Okay. So I have.
And I also did understand this point you made about the inverse Wishart assumption. Like where is the assumption going?
Oh, it is going in the computation. So like when we sample, so we are trying to predict, we're trying to predict PIs, right? We're trying to see which one is the highest. We make a prediction about the final point, starting from say at the jth batch, we make a prediction about what the probabilities are going to be, what P1 is going to be for the kth instance, right? And if I see P1 is the highest, then we say that the first candidate wins. Right. Now, in making these predictions, we have some assumptions about a prior distribution. Prior for mu. Mu is, as I said, a function of PIs, like a transformation, which is a variance stabilizing transformation. Now, we try to predict mu because it's a one-to-one function of PIs. So we assume some prior distribution for mu. We assume some prior distribution for sigma. Okay. Now, inverse Wishart, why are we using? Because it helps it's an easier computation for the posterior distribution given the jth round of data. I'll come back again. Let me just discuss the data because I haven't talked about theorems at all. Okay. So we see that there are 52 constituencies which are very closely fought. This is 23 plus 29. And in 41 of them.
Question in the chat.
Yeah. Okay. Can you read it out? Is that?
You just did on the chat.
Yeah. Are we working with, isn't it standard? Yes, that is true. When we are working with multinomial data, it is standard to use a Dirichlet prior. That's the conjugate prior for multinomial as like beta is for a binomial. But here we have transformed it because there was too much error in the coming out of the variance when we are working directly with the proportions. So we have transformed it to a form and then use something called the delta theorem to use a multinomial approximation, the multivariate normal approximation. So when we work with multinomial directly with a Dirichlet prior, then our predictions are much worse. You read. Oh, no. Okay, and in two of them, of course, we cannot make a call. Now, on an average, we see that for these closely fought constituencies, we have 70, we require more votes to be counted to make a call. And out of them, for the ones where it's slightly higher, on an average, we have 60% votes counted. Now, in 4 out of these 34 constituencies, our methods predict inaccurately. And for the rest of the constituencies, we see that 156 of 157, our prediction is perfect. And there, the proportion of votes required to make a call is also quite low, in the sense that we have we have a hard restriction of 50%, and then we require only about 5% at most to make the calls. And well, as you can see, the size of the constituency doesn't really have a considerable effect on the prediction accuracy. Okay, and now let me go back to our model. That's what we have questions on. So, once again, reformulating, we are interested in the parameters P1, P2, PC minus 1. There is an issue, which is that the variance of these estimates involve the parameters themselves. So that's why we have a variance stabilizing transformation. The variance of LJs by themselves are constant. We have a transformed form of it, a form of central limit theorem with a scaling of square root of NJ. Then we have a variance of that. Now, so now we are, of course, we are still interested in P1, P2 going up till PC minus 1, but we are now more interested in mu's, which is sine inverse 2P1 minus 1, sine inverse 2P2 minus 1. So if we can predict them, then we are essentially predicting P1, P2, and so on. So we are working with mu, and we are using a Bayesian methodology in making our predictions. So we assume that mu follows a multivariate normal with a certain, that's a prior distribution with mean alpha and variance sigma p. And further, the sigma p again follows in, so that's the hierarchical Bayesian framework where we assume that sigma p also follows inverse Wishart distribution. We can again further assume alpha follows a normal distribution with certain parameters again. Yeah. And again, we use sigma follows inverse Wishart distribution. This is for multivariate normal. This is the standard conjugate prior that is used in the literature. So based on every round of a data, we have an estimate of mu, which we go on re-estimating after we get more and more data. So we have an estimate of posterior mean every time, and we can show theoretically that this posterior mean converges to the actual true values. Now, we had something called L1 to Lj, N1 to Lk, as k goes to infinite. So what is L1 to Lk? L1 to Lk, this is the data for every round. And we can create a sigma field based on that. That's denoted by Fk. Now, what is posterior mean? There is a form of the posterior mean, which is based on the prior for mu, alpha, and the data that we have, and Ni, Li. Okay, Ni is the size and Li is the data that we have of the information. This is a form of posterior mean for multivariate normal that we have. Now, as you can see that as the size, and this is again scaled by n sigma inverse plus sigma p inverse, and as you can see, as the size of data increases, as we have more and more data, then the contribution of alpha and sigma p, they are negligible. So it is, the prediction is primarily based on the data. So the prior does not have that much of an effect in the final predictions, and that's what we want to theoretically again show. So for that, we use certain inequalities, use some matrix inequalities and general triangle inequalities. So we break up the mean into 2 parts and use some matrix transformation. So what we have, so I'm just showing one of the proofs, which is the first one, equation 8. This is what I'm going to prove. Equation 9 can be shown similarly. So mu PM, that's posterior mean minus mu naught. I have broken it up into two parts using triangle inequality. So one involving alpha and mu naught being the true mean, and the other is the data minus mu naught. Okay. Now for the first part, we use a matrix transformation. So then everything essentially depends on I minus sigma p times sigma p plus sigma over n inverse. Now, as n goes to infinity, which is number of folds, if the number of batches or number of instances go to infinite, of course, that will also go to infinite. So that means that whole term before that becomes identity matrix minus identity matrix times alpha minus mu naught, so that is 0. So consequently, the expectation of that will also go to 0. So we can argue that that part in the triangle inequality, that the probability of that being large is going to 0. And the other part, which is again Li minus mu naught. Now, as you can remember, that's like there was a central limit theorem based on that. So Li minus mu naught, if mu naught is a true value, then Li minus mu naught with sufficient transformation that follows square root of n times the normal, the normal distribution. Now, expectation of this whole variance part that can be transformed ultimately to show that that's upper bounded by Ck, which is capital big O of 1 over n times something that's a constant, because that's like the variance of the prior. So we can show that that again goes to 0. And so we can write this second part, the probability of like this whole thing, that again being large is going to 0. So both of these terms are going to 0. So we have a convergence in probability for the posterior mean to the true value. Okay, and similarly, we can also show the variance. I'm not doing that. It's kind of a similar argument, only again using matrix inequalities. Now the sample. Now the posterior that we obtain is difficult to sample from this posterior. So we need some conditional posterior distributions of mu, sigma, and sigma p. So for all information given in the jth instant, if that is denoted by fj, then we can find the conditional posterior of sigma, sigma p, and mu. And since we are using conjugate prior, so again, they are inverse Wishart and normal respectively. Okay, so this is a sampling from the conditional posteriors. And prediction. So how do we make predictions? So for predictions, we want to have the expectation of LG. LG is the data till the jth instance. And the posterior predictive distribution is something that has a mean, which is expectation of LJ given FG. And similarly, it has a covariance. Now, it is difficult to get a closed form expression for these expectation of variance. So we use a Gibbs sampler to simulate from this posterior predictive distribution. Now, once we have a posterior predictive distribution, that naturally means that we have an estimation for mu's. Now, if we have an estimation for mu's, then we can transform back to that functional form back to our PIs. Okay, all right. So we can approximate the mean of posterior predictive distribution from the data, and we can also approximate the dispersion of them. So we can draw samples from this posterior predictive distribution. So essentially, we have an observation. So that's the prediction part. Now we have also tried this. We have tried our model on different simulated forms of data with varying sizes, varying number of categories, varying number of instances, and varying number of batch sizes. Okay, We have taken different forms for epsilons, the fluctuating part, the random part in our model, which is the fluctuation in the cell probabilities. First, you have taken a simple situation where these are all taken to be 0. Then we have also taken an instance where each of them are multinomial random variables with 0 mean and dispersion that goes to 0. And we have also imposed dependence across different coordinates. So across all the different categories, we have used some dependence based on a randomly generated PD matrix. So in each of these situations, we have done a simulation study, and our accuracy is pretty high in there as well in making the final calls. So I mean, they are also presented in our paper, which I'll have a link at the end. So you can see the results themselves, but we have varied across different choices of the number of categories, the number of batches, as well as the batch size. Okay. All right. So that's these are some of the simulation results. So when so there are 3 different data generating processes, as I have said, one where epsilons are all 0, one where epsilons are multivariate normal but independent across categories, and one where there is dependence. In each of these situations, as we can see, with changing batch size, our predictions become higher and higher. And each of them are essentially reflective of different data situations that we deal with. So as I said, I mean, apart from the data that we have, that I have just shown, I also have used another data, which is county bias data from US elections. So some of them had much smaller sizes, so that's why I have to emulate this for such categories as well. And as you can see, when there is all the epsilons are 0, then we have correct calls even with very small batch sizes. Of course, as the batch size increases, then our proportion of correct calls increases as well. Even when we have random fluctuations, we have quite a good proportion of correct calls even for a batch size of 5,000. It's become slightly more difficult when we have dependency. And when there is dependency, there is a much larger proportion of no calls. So we are never able to go through that threshold, which is too early to call, as well as too close to call. So these are our simulation results. And that's what I wanted to talk about today. So this is our paper. So it got accepted in the Journal of Forecasting. It primarily, I mean, this is only on electoral predictions. As I've said before, we also tried it on another data set, which is market size predictions, but we didn't publish that result. It's work with 2 electoral data sets. Okay, thank you.